Preview of fundamentals to plot internal forces. We will discuss simple beams. Concentrated loads, different types of them, and distributed loads. Welcome back. We will discuss some fundamentals on which we can build the solution of all our future examples. Let's first consider this simple beam. Those two supports are end supports. Our first example has a concentrated load in the shear direction, perpendicular to the axis of the beam, acting at N, and the force is of value P. The point N divides the total length L of the beam into L1 and L2. We have our reactions YA acting at A, YB and XB acting at B, but XB has a value of 0 in our case. To compute the reaction YB, we simply take a moment about A, and we have PL1 minus YB multiplied by L equals 0. This means that to get a moment of a force, we must multiply it by the arm, which is a length perpendicular to the force and reaches the point at which the moment is taken. So the arm of P about A is L1, the arm of YB about A is L. And we have our equation here. PL1 has a positive sign, while YB multiplied by L has a negative sign. This is because both of them rotate in opposite directions about A. We have our structure here. P rotates about A in this sense, clockwise. YB rotates about A in this sense, counterclockwise. So they have different signs. Now we will deduce our value of the YB. YB equals PL1 divided by L. Similarly, if we take moments about B, then P1 has the arm L2 to form a moment, and YA has the arm L to form a moment, and they rotate about B in opposite directions. It doesn't really matter which is positive, which is negative, because our equation is equal to 0 at the end. YA is PL2 over L. Now we will plot our shear force diagram. QA, shear at A, is the value of YA, very simple, PL2 over L. Now please note that we have our center line here. We are plotting our shear force, so we are searching for all forces perpendicular to the center line. Remember, we discussed before that if we have our elemental beam, this is the notation of the positive shear. The positive shear was perpendicular to the center line. In more accurate or scientific words, it is the force in the plane of the section of the beam which is perpendicular to the center line. We start by YA, which has this value, and from A to N we encounter no perpendicular forces, so the line keeps parallel to the center line of the beam till just the left of N. After we move to the right of N, the force P is included
and must appear in our equation. So Qn right equals the last computed shear YA minus P. We subtract P because it is heading downwards. Since we started our computations from the left of the beam at A, then the forces heading upwards are positive shear and those heading downwards are negative shear. YA minus P is really minus YB. And the red line here is the value of the applied load P. Note that on the diagram, we only write force values measured from the center line of the beam. From N to B, we encounter no shear forces and the plot of our diagram is parallel to the center line until we reach B and encounter YB heading upwards, and therefore the diagram heads upwards too. We conclude that our diagram closes, which means that we computed our vertical reactions correctly. The value of the load P is really the difference in the values of shear between Qn right and Qn left, respecting the sign convention. Bending moment diagram. Moments are not accumulative as N and Q. They are computed at sections of load variations, and each two adjacent sections are joined together. Note that A and B have zero moment as they are an end roller and an end hinge. And we are left with section N having a variation of load. So if you compute Mn from the left of N, we have a section at N and consider all forces in this ellipse. We have Mn left equals Ya multiplied by the arm until we reach N. If you compute from the right side, we consider again a section at N and include all forces in this ellipse. We have Mn right equals Yb multiplied by L2 the arm until we reach N. Notice that we have the same value of Mn no matter which side we compute from, and we plot our diagram. What we really plotted is three values of moment: a 0 at A, a 0 at B, and the value of Mn, and we simply joined every two adjacent values together. Let us consider the area of this blue rectangle. In other words, consider the integration of this part of shear diagram. The area is PL2 over L, the height of our rectangle, multiplied by the length, L1. The computed area here is really the value of the moment at section N. This means that the moment can be computed from integrating shear. However, this can be tedious if you have a complicated shear diagram. I believe it is better to compute the moment at each section using force by arm. In other words, considering all moments at one side of the section.
Let's have another example. We have still our simple beam, but this time we have a concentrated moment at M. The reactions still Ya and Yb, sigma moment about A. We are standing here having the moment at A, M, and rotates about A, and YB multiplied by the arm L rotates about A in a different sense or in the opposite direction, opposite than the force or the moment M. Here is our equation. YB equals M over L. Now having sigma forces of Y equals 0, YA plus YB equals 0 gives YA equals minus YB equals minus M over L, which means that we estimated the direction of YA in the opposite direction. We just cross it out and have the correct direction with the correct value of YA. Shear force diagram. We simply start from the left-hand side. Forces heading upwards will be plotted above the center line, and forces heading downwards will be plotted under the center line of the beam. And the shear force is accumulative as long as we are passing through our beam. So let's have the shear at A equals minus M over L. We'll plot it downwards. Until we encounter B, we have no forces perpendicular to our center line, and therefore this value will be constant till we reach B. Finally, we encounter YB heading upwards. We head upwards and our diagram closes. Computing the moment, the bending moments, we will compute two moments at N. One of them considering the left part of the beam, and we'll simply have all forces acting in this circle. So M N left equals M over L multiplied by the arm L1, and will be plotted upwards with the tail of the force causing the moment. Now, if you consider the right side, we will have a cut here. We will consider all this right side. We have YB multiplied by the arm L2 and will be plotted downwards with the tail of the force causing the moment at the right of N.
Simply we connect the values of those two moments with this red line. Notice that the value of the moment M is the difference between M right and M left at section N. M right is positive, caused by YB multiplied by L2, while M left is negative, caused by YA multiplied by L1. The difference between the two values is really the applied concentrated moment M at N.
Now take this simple beam with a concentrated normal force equal to H. Of course, we have the reactions XB. We don't have a YA or a YB simply because if we consider a moment about A, we will have, say, YB multiplied by L equals 0, which gives a 0 YB. Similarly, a 0 YA. XB equals H. This is our only reaction. Plotting the normal force. We have our normal force equals 0 from A just to the left of N. The right of N, H appears and is a compression till B and our diagram closes. Of course, we add that the normal force equals 0 left of N. Note that this red line has a value of H. It is really the difference between the normal forces just left and right of N. Please notice the effect of the concentrated loads on the corresponding diagrams. The first diagram, we have a concentrated normal, and therefore in the normal force diagram, we have a red value at N equals to the concentrated applied normal. The second case, we have a concentrated shear. A drop is observed in the shear force diagram of value P. The last case, we have a concentrated moment. A drop of M is observed in the bending moment diagram. Finally, let's go to the distributed load with the intensity W ton per meter run on a simple beam. The reactions, before going to the reactions, we will have WL instead of W ton per meter run. We will have this virtual resultant to compute our reactions easily. So we have the reactions YA and YB. Since we have no XB and our structure is then symmetric, each support will have a reaction of half the load WL over 2. Shear force diagram. To compute our shear force, we have a section at X. We will have a section here at a distance X from the very beginning of our beam. And therefore, we have a concentration, a virtual concentration of the load of Wx for this part. Our shear will be the value of YA minus Wx. This is the shear at the section, the red section drawn here. This is a linear equation with the variable x. At x equals 0, Q will be WL over 2. At x equals L over 2 in the middle of the beam, just remove x and substitute with L over 2. We have Q equals 0. At x equals L, we have a Q of minus W L over 2. Which means we will have a straight line with these values. Finally, we encounter the YB upward. We just go and our diagram closes.
For the moment, we have the bending at section X of this equation. Mx equals the reaction at A, WL over 2 multiplied by X, minus the virtual concentration of the load Wx multiplied by the arm X over 2. This is a parabolic equation. At X equals L over 2, we substitute for X by L over 2, and we get a bending moment of WL squared over 8 in the middle of the beam. We just plot it here.